All right, so now welcome to the second portion of the kinematics lectures in the class, and this is going to be angular. Um, Now, the angular component of kinematics is what we generally use to describe most of human motion. This is how we're going to compare because it gets down more to the independent segments in your body, as opposed to just thinking about the entire system as one point or one center of mass. So the outline for this presentation are going to be, we're going to talk quickly about the definition, talk about types of angles there are, the units of measurement for these angles, and then we'll get into the angular motion and how did you discuss angular motion. But then it is a very important concept, and it's converting some angular motion into a linear components of that motion, or the result of that linear angular motion. What we're going to do is we're going to use the knowledge from this lecture to discuss running, cycling, and swimming. How do we use that more than just linear is because most of the linear kinematics, when we talk about the human motion, is going to take whatever segments or the body as a whole and bring it down to a single point, the center of mass of that individual segment or the body. When we discuss human motion, we're more interested in what's happening at a segmental or a joint angle level, so we can dictate or determine what's different between person one, person two, or over time. So as you see here in the silhouettes, many of these individuals run differently. Some are leaned forward more, some have greater knee flexion right before foot contact, some have more extended legs as they approach terminal stance. And these are all going to be ways that you can describe it. You either say you have a greater forward trunk lean. If you look at the elites on the right, majority of them all have the same forward trunk lean. Well, the guy in the very back is standing much more upright. He has what we call a more erect torso or a more extended torso. So these are all ways that you're going to describe it. And what you'll find a lot of times is that the majority of the elite runners have a much greater stride and higher stride frequency, but they also be able to push off with center of mass much further in front of their trail leg. Now, when we go to the cycling world, a lot of it comes down to the bike. So, in positioning of the bike is a huge component. When you talk about a TT bike, which you have here, or a triathlon training bike or time trial bike. So TT stands for time trial. It's also known as a triathlon bike. But you'll find this Argon 18, just so you know, a reference point, is $10,000 because of the components that make up the bike. And you can, I've found bikes upwards of 15,000 depending on what is all included on it. But what you have here is you have two different bikes, and they're silhouettes of bikes. And you have a traditional road bike, which is the black one, which has the seat post, which is that post that comes up that the seat sits on top of, lean back more. Where you have a time trial bike or a triathlon bike, which has a much more vertical aligned seat post, and the shaft of the frame is much more flat in a TT bike. And what does that for? Well, it's to produce a more aerial and more forward positioning of the body. Most triathlons are non-drafting, and that means that you can't ride behind somebody else and be pulled by the drag or the draft that's created behind them. So therefore, you have to put yourself in more of an aerodynamic position, which allows you to go faster and work less. So that's the whole positioning and the idea behind these triathlon bikes. So to define angular motion, we're going to do it in a couple of different ways. Firstly, just angular motion in general is when all points move through the same angle in the same time, as opposed to what we talked about with linear, where they move through the same distance or same displacement in the same amount of time. Here, they go through the same angle. So you have an axis, and along the rod or along the segment or joint, every point along that goes to the same angle. Now, it doesn't mean they go through the same distance, but they go through the same angle of motion. Now, when we talk about human motion, it's going to be very similar to whatever this is, a cartwheel or, I don't even know what another term, round off or whatever you call that, but there's rotation of the system around the axis, where it's the hands on the portion. So the feet are going through a greater displacement, but they're going through the same angle as the head is. But you also have a translation from point A to point B of the whole system as a whole. So when we talk about the types of angle, there's two general types of angles. There's going to be an absolute and there's going to be a relative. Now what we're going to do first is go through the absolute angles. And these are the segmental angles. So your thigh, your hip, your arm, your trunk. And what these are going to be is they're referenced to a right horizontal typically. Now there is ability to have them referenced to the vertical, and we'll also often do that with the trunk, where you'll have a forward lean or a backward lean, and they'll do that to the vertical. But you need to make that known when you're doing the analysis that you're doing it to a vertical as opposed to a right horizontal, because generally it's understood to a right horizontal. Okay, it's often done to the distal end of the segment, but you can do it to the proximal. You just have to make that known. But the typical and the traditional method is the distal end. And then you do a counterclockwise as a positive motion. So when the motion goes from a counterclockwise, and you see all these angle A, angle B, angle C, angle D, they're going from the right horizontal around clockwise to the segment, and that is a positive angle. So a way to do this when you're talking about a coordinate system is what you'll see here is you have an XY graph with the 0, 0 origin, and that's our global coordinate system. Now what we're doing is we're going to do the proximal and distal ends of, say, the thigh in that global coordinate system, and you can figure out what the thigh angle is by calculating that triangle. You can either do it by calculating the triangle on top. So the other angle that we're going to talk about is the relative angle. Now, these are the joint angles: your hip, your knee, your ankle, your elbow, those type. And so these are formed by two segments or two straight lines that intersect at an axis, and we're talking about that form between the two. Now to calculate a joint angle, you can do, going back to that global coordinate system, calculate the angle between the two, or you can do proximal segment minus the distal segment. So if I know the thigh angle and I know the shank angle, I can calculate the knee angle by the thigh angle minus the shank angle. Or you can create the triangle between x1, y1, x4, y4 in the axis location. Do it that way. But it's easy if you calculate the two segmental angles, you can calculate it very simply. So the idea is that we can describe the same motion using two different angle orientations, right? So now you have the same runner here in A and B, and I can describe it differently using either the segmental or absolute angle versus the relative or joint angle. If you've already decided and figured out which one is which, then you're ahead of the game, right? So A is going to be the relative or joint angles because it's that describing the elbow, hip, knee. So it's describing the angle formed between two segments with an axis, where B is representing the segmental angles. So you have the thigh, the shank, and the torso. Both of the all now, if you look at that, they're all towards, in our reference here, the left horizontal, but just imagine that person running the other way, and it converts to right horizontal as well. So depending on how you orient that is what we would discuss. So the units of measurement, they're basically three. We'll talk about degrees, radians, and revolutions. So degrees are basically just an arbitrary unit of 0 to 360. 360 is a full revolution, which is down there on the bottom. Revolutions you'll talk a lot about when you talk about cycling. Those are where the revolutions come in a lot. A revolution of the pedal, a revolution of the wheel. And then you have radians. Now radians are a fundamental ratio, right? So 1 radian equals 57.3 degrees. That's how you're going to do the conversion. What is a radian? Well, it's the angle at the center that represents the arc length that's equal to the radius. So whatever the radius of your circle is, there's an angle that the circumference or the arc length on that circle is the same as that radius. So that is what the angle of the radians. Now, it's very important to understand radians are unitless. So when we go further here, you're going to understand why that's very important and why, for a lot of times, you're going to start referring to radians and converting everything to radians. When we deal with the conversion of angular kinematics to linear, you need to do it in radians because of that unitus concept. So here's just a little depiction of the units of measurement, revolutions versus 360. The circumference of a circle is 2 pi r radians. So 2 pi r radians. And then you'll have just different conversions. Now here's what that radian looks like. So 1 radian, which is represented by theta. So theta could be degrees, it could be radians, it could be revolutions. R is the radius from the center to the circumference, and S is that arc length. So 1 radians equals the arc length divided by the R. So it's that ratio of the arc length divided by the R. Now it's very important that you understand the direction of angular momentum is determined by this right-hand rule. So how you do the right-hand rule is you take your fingers of your right hand and you curl them in the direction of motion. So whatever the direction of the motion is, and you can see on the figure on the right, he's moving the fingers in the direction of the motion. Whatever way your thumb is pointing, that's where the angular momentum is positive. Generally speaking, for human motion, rotation counterclockwise is a positive direction. So when you talk about a motion similar to the one on the right here, the dancer, that would be a negative rotation producing a positive angular momentum downwards. Okay. So now we're going to get into the individual portions of angular kinematics, and the good news for you is they're exactly the same as linear kinematics. They're just dealing with angles instead of the linear component, right? So position, it's the object's position relative to the defined reference system. Distance, it's a scalar again, so it's a total path traveled. There's no distance or no directionality associated with this. But then you have the displacement, which is that change in angular position. Now this has the directionality, so it's important to understand that the counterclockwise and clockwise motion comes into play here. Therefore it's a vector. It's final minus initial. It's not the total path traveled. How does this play out? Well, so here you have a pendulum, which is often used in angular motion because every point along that string in that ball or that rigid rod in that ball move through the same angle but a different displacement or different distance. So when you look at this, so it goes from 0 to 70 back to 35, the total path traveled, or the total distance, angular distance, is the total path. So 70 plus 35 degrees, it's 105 degrees total. But as you can see on the diagram here, the displacement is only the final position, which is 35 degrees, and between the 0 degrees, so 35 minus 0. Now the question becomes, why is this positive? Well, that's because it is going in a counterclockwise from start to finish, right? So if we switch this and it started at 35 and ended at 0, then it would be a negative 35 degrees, but the counterclockwise portion of it caused it to be a positive. So remember, this is where that counterclockwise and clockwise comes into play because that directionality of the movement is very important. Well, how do you convert that to radians? Well, here you go. So the radians of that, it moves 35, you divide it by 57.3, and you get 0.61 radians is what it moved. Now, again, it would be negative 0.61 radians if it went the other way. So here you have angular velocity. We're not going to spend a lot of time. It's the same as the rate change of angular displacement with the delta theta over delta t. And if you have the instantaneous, it's theta I plus 1 over theta I minus 1 over 2 delta t. And again, remember why I use delta t. 2 delta t is because basically we're doing snapshots, and they're all the same distance away or same time away from each other. So whatever your sampling rate is what determines what your delta t is. Here we have angular acceleration. Okay, so the rate change of angular velocity, same thing, radians per second squared, degrees per second squared, revolutions per minute squared. Now, angular acceleration is this alpha, and I forgot to tell you the angular velocity is that omega. And then for displacement or distance, we always use just theta, depending on what you're using. Okay, so here you have the same thing, average and instantaneous. The next step for us is to continue our progression and connect the angular component of kinematics into its linear counterpart. And we do that by a very important term in condition, and it's the radius. So those are the points along the line relative, to the axis is going to determine the linear speed, linear displacement, linear velocity, linear acceleration along that forearm. So the forearm here has 2 points that we're going to talk about, S2 and S1. It has R2 and R1. So as you can see, R1 is greater than R2. They both travel through the same angle. But here you have S1 and S2, and you can definitely see that S1 has traveled through a greater displacement than S2. How do we quantify that? Well, it's a simple relationship where you have the theta, or the angle which the arm goes through, equals the arc length, or the linear displacement, divided by the r, the radius. Now, it's going to be very important. We're going to rearrange this so it says the s is going to be the theta multiplied times the radius. And that's how you're going to determine it. So it's a multiplication of the radius times that theta, and it determines the s. Now, it's very important for this process that we understand that the theta needs to be in radians. Well, why radians? Well, radians are unitless. And so if you multiplied, say, a degree by the radius, which is a meter, you'd have to have the s in degree meters, which is not what we want. For the linear displacement, you want it in the position or the change of position units. And that's going to be meters, or inches, or centimeters, or whatever it is. So if the theta is radians, that's unitless, so you'll be stuck with whatever units the r is. So your s is going to be in the same units as r, as long as your radians are unitless. And so for all these angular linear connections, make sure that your radians are unitless. If you do it on the test or any equations or problems, and you keep that angle in degrees, it's going to be wrong because if you go back to your units. So to go forward, and where does this come into play? Well, so yeah, it goes through greater displacements the longer the club. And here you have your clubs, right? So you have single iron clubs, length on the right, the left is the standard clubs. And why do we play with the left standard clubs? Well, because the head of the golf club goes through a greater displacement, there's going to be a great conversion from that to the angular velocity. And you'll see that here in one moment. But the reason we do that is because we try to get a greater club head velocity at contact with the ball, which is going to transfer to a linear velocity of the ball at contact. The same thing with the crank length. So the crank length, it's thought that the longer the pedal from the axis of rotation, it's going to produce a greater velocity. Well, when we do some power analyses, and that's what this graph represents, is some power analyses, because power comes down to force velocity, which is essentially power is work over time, which is force distance over time. Well, the change in distance or change in placement over time is going to be velocity, so you just multiply force times velocity. Here we find there's an optimal length for these crankshafts. For this one, it looks like 145 and 170 are significantly different than the other three lengths on the group that they looked at. Keep in mind, it's only a 50 maximal power output. Does that transfer to a triathlon? Not really, because triathlons you're not going to be producing maximal power. These are more sprinting events where your maximal power is going to be up as high as you can. Or if you do some of the studies here at UNLV and you do some of these physiological studies where you're trying to produce maximal power output, that's where you're going to come into here. But the crank length is designed to give you a mechanical advantage to increase your velocity of the pedal in the stroke of each pedal. The velocity component here is going to be just a normal v, and we're going to talk about it as a tangential velocity. Now, there's only one velocity component. It's tangential. It's mean the linear velocity is tangent to the curved path. What does that mean? On this graph here, you see all the red vectors. So you have, say, the blue line is the radius of rotation. So that is, say, your crank length. You'll see the omega there, which represents the counterclockwise motion, the positive direction of the angular velocity. And then you'll see the VT. V sub t is going to be what we're going to use for the velocity tangent. It's at a 90-degree angle from the radius in the direction of motion. So that is a linear component. So think about the golf swing again. You think about your club head. As my club head strikes the golf ball, it goes linearly at a 90-degree angle from the rotation of the club straight out. That's how we do our rotation of a golf swing. The ball goes in front of us or off to the right, depending on our club head, but it's going to go out a 90-degree angle from where it's being contacted. We can calculate that by using Vt equals r, which again is the radius, times the angular velocity at that contact. Okay. Now again, this only works with radians. So your angular velocity has to be in radians per second or radians per minute or whatever unit of time you're dealing with. But the angular velocity needs to be in radians for this to work. So the last one is going to be acceleration component. Now there's going to be two components here. There's a centripetal and a tangential. Okay. Now this is going to be the tangential is the same as the velocity tangential. You'll see there is the AT going at a 90 degree. The centripetal is also termed radial, and this is the direction. Sorry, we're going to start with tangential. It's the same as the direction tangent to the curved path, but again radian. So here it's AT equals r times the angular acceleration. So tangential velocity and tangential acceleration are very easy. They're the radius times the angular component of whatever it is. So whether it's angular velocity, whether it's angular acceleration, that's the tangential. Centripetal acceleration is also called radial acceleration. So you'll see I have it here in brackets as either a sub c or a sub r. You're going to see it both. It means the same thing. Centripetal meaning back towards the axis. Radial meaning along the radius. So it means the same things, but it's traveling towards the axis of rotation. So here what it's actually going to be is you'll find a sub r or a sub c equals the radius times the angular velocity squared. So this one you're not going to use the angular acceleration, use the angular velocity squared. In centripetal acceleration simply is even if you have a tangential acceleration not changing. So if your tangential velocity is constant and it doesn't change, means that your tangential acceleration will never change. But think about it. If you're going in a circle, you're always changing the direction of the motion. Therefore, the centripetal acceleration or the centripetal velocity is always changing. So there's always going to be some sort of acceleration that's keeping you in that circular path. Because if there wasn't a change in the centripetal, the velocity leaning back towards the axis, then it would go off in a straight line, and it would never stay in that rotation about the axis. So there is always going to be some sort of centripetal acceleration. Now we can go further and talk about the total acceleration of the system, and it's just simply the sum of the tangential and radial or centripetal. So here you have the total linear acceleration is a combination of the centripetal acceleration plus the tangential acceleration. And then here you have that AR, which is the vector addition of the two. So you're going to complete your triangle. You have your rotating segment that goes off in the direction at that point by converting and calculating the resultant of AC and AT that'll give you the direction of the acceleration throughout the process. So that's going to be the end of this lecture for angular kinematics. So go ahead and take a quiz. And then what we're going to try to do this week is I'm going to bring in possibly some literature papers, and we'll talk about some stuff. And I want to talk a little bit about the Ironman items that I posted online to see if those help you out a lot. understanding some of the concepts and how to apply what we've gone over here in class to the Ironman in Triathlon Worlds.